Hello everyone, welcome back to Life Technologies YouTube channel, and thank you so much for watching and supporting our content. So this is another episode of our Huawei Lab simulation series. Remember, in this series we discuss and demonstrate how to implement different networking protocols or different networking technologies on Huawei routing and switching devices. So if you're interested in learning how to configure and troubleshoot different networking protocols like OSPF, ISIS, BGP, MPLS, and many other technologies on Huawei routing and switching devices, kindly check out this series on our channel. And if you are watching this video and you are yet to subscribe to our channel, kindly hit that subscribe button to stay tuned in for more upcoming videos. So in this episode, we'll be discussing a very important feature of BGP. We know that BGP is a very common networking protocol, especially for service provider networks. Due to its flexibility, it brings in controlling the traffic flow between different autonomous systems. So in this episode, we'll be focusing on how to implement BGP ORF, outbound route filtering on Huawei routing devices. So whenever you have BGP running on the network, you need to have the route export and import policies configured between the routers. So assuming that in this setup we have AS100, which is the customer network, and then we have AS200, that is the service provider networks, we will be configuring BGP between R3 and R2. So we are using BGP as our PCE routing protocol. And once we have configured BGP as our PCE routing protocol, we also need to configure route policy that will control the route exchange between our CE, which is R3, and the PE, that is R2. Many times there are so many routes that needs to be exchanged, of course, but we don't want to receive everything from the service provider. And sometimes also we don't want to receive the default route. So we need to have a mechanism that will help us to efficiently exchange the routes between our CE router and the PE router. So that is where outbound route filtering feature comes in. So with outbound route filtering, this one will enable a BGP device to send local routing policies to a BGP peer. So in this case, we have R3, that is the local device, and then we have a remote device R2. So R3 will send the locally configured policies to R2, telling R2 that I only want to receive these specific routes. Now, R2 will not advertise everything to R3. R2 will make the export policies based on what it has received from R3, and then it will only advertise the routes that R3 has requested. So it's like R3 is requesting R2 to only send specific routes to it. Then R2 doesn't have to configure so many policies to control the route exchange between the two routers. So these are very common application, especially when you have a connection to the carrier network and you only expect the carrier to send only some specific routes to your local router. And many times the carrier doesn't want to maintain many routing policy. Like you want to, let's say for example, you have this setup, you have you have 4 servers, you have server 1, server 2, server 3, server 4. So maybe from the beginning we had only 2 servers, server 1 and server 2, that were active, and R2 was advertising these routes to R3. So if R2 had configured policies to control the route exchange, and then we have added another server, it means R2 has to change, maybe has to add these prefixes to the routing policy so that these routes can be advertised to R3. But with ORF, R3 will request. R3 knows that there is a new server in the internet that they want to access, so they will request the route from R2. So we add it on the prefix, and once we are sending our ORF to R2, we tell R2 to include this prefix to the route that it's advertising to R3. So it's like R3 request routes on demand. We are only requesting routes on demand. When we want this prefix, we tell R2 send us this prefix. When we don't want it, we can remove it, and then the refresh message will be sent from R3 to R2 without that prefix, and R2 will stop advertising that prefix to us. So the main key advantages of ORF: it prevents the local device from receiving a larger number of unnecessary routes, because you're only requesting for what you want. So it's helping to control the number of routes that you are receiving. It also reduces the CPU usage of the local device. Remember, if R2 is sending all the routes to R3, it means R3 will have to use a lot of memory or CPU to process these routes. So this one will help to control or to reduce the CPU usage on the local devices. It also simplifies the configuration of BGP peers. Remember, I mentioned that when you have ORF, it means you don't have to configure so many export or import policies on the router on R2. You only need to define the prefix that you want on R3, and then R3 will be able to request these prefixes from R2. So those are the main advantages of ORF, and in this lab we'll be demonstrating how you can use ORF to control route exchange between R3 and R2. So you can see that from this topology I've mentioned that we have two autonomous systems, S100 and S200. S100 has two routers, R1 and R3. We are using OSPF as our IGP, and then we have three routers in S200, which is now the service provider network. We also have these different servers, and when you don't implement any ORF feature, it means all these routes will be propagated towards R3. So R3 will get all these routes, but once we implement the ORF feature, we will be able to control which routes should be advertised from R2 to R3. So to start, this is the topology in ENSP. And we have already implemented the basic OSPF and BGP features. So starting with R1, I will undo terminal monitor. We can display IP interface brief. You can see that we have configured these interfaces with the necessary IP addresses. Can display OSPF neighbor, OSPF peer. You can see that we have a peering session between R1 and R3. On the same, we can see the OSPF configuration, display current configuration, OSPF. These are our OSPF, very basic configuration, OSPF process 10. We are all running in area 0, and then we have advertised the loopback IP and the point-to-point IP. Next to R3, we also have OSPF running, display OSPF neighbor. We have a display OSPF peer. We have one peering session to R1, and if we check the OSPF configuration OSPF, you can see that also just basic configuration, we are advertising the necessary networks. So after this, we can also verify the interface configuration, display IP interface brief. You have IP addresses configured on these interfaces. We have also went ahead and implemented BGP between R1 and R3. So starting with R1, I display BGP neighbor, display BGP peer. So you can see that we have a BGP peering session between R1 and R3. These are the configuration, display current configuration BGP. These are the configuration, very basic configs. We are using loopback 0 IP as the source interface for BGP P establishment. On R3, display current configuration BGP. You also see that we have BGP 100 configured. We have two peering sessions, one to R1, which is iBGP, and another one to R2, that is for the eBGP peer relationship between the two. So display BGP peer, you can see that we have two sessions established, one to R1 and another one to R2. On R2, we also have the same display BGP peer. Now we have three peering sessions, of course, one to R3, another one to R4, another one to R5. We are also running OSPF, display OSPF peer. You can see that we have two peering sessions for SPF in area 0. This is for R4 and R5. So between R3 and R2, we are purely running BGP. We have configured eBGP peering relationship between R3 and R2. These are the servers. The servers are simulated on the routers using loopback IPs. So display IP interface brief. You can see that we have loopback 10 and loopback 100 with the configured IPs. On R5 we have the same display IP interface brief. We also have loopback 10 and loopback 100 configured on these routers. When we check in OSPF, let's check the OSPF configuration on R5. Display current configuration BGP. You see that we have advertised these networks into BGP because we have 210 and 200. 220 is not there, you can ignore it. Then on R4, display current configuration BGP. We have these networks advertised. This is 100 and 110 that are configured on these interfaces. So once we have configured the necessary network that we need to advertise, and we check on, if I display BGP routing table, you can see that we have these networks. We have the two networks, 100.10, 200, 200.10, and these are the details. So when R2 has these routes, definitely all the routes will be advertised to R3. So from R2, we can display BGP routing table, PI it's 10.10.10.2, and then check the advertised routes. You can see that all these routes are being advertised from R2 to R3. From R2, all the routes are propagated to R3. So no matter how many routes you have in this ISP network, all the routes will be propagated to R3. And you know that we have so many routes on the service provider networks, and R3 may not need all these routes. So on R3, we can check the received route, display BGP routing table, peer 10.10.10.3, received routes. See that we have these three routes. The four routes have been received on R3. And on R1, we also have display BGP routing table. We have the four routes have been received on R1. Of course, on R3, we have configured next hop to be local. Configuration BGP. So we have added this next hop local towards R1 so that this one will always change the next hop to itself when it's advertising the routes to R1. Remember, when the routes are advertised to iBGP, the next hop is never changed. So for us to be able to advertise, to install these routes on R1, we need to change this router to be local when it's advertising any BGP routes to R1. So with this in place, you can see that we have all routes exchanged. Whenever we have a new route, a new prefix added on the service provider network that is in S200, this route will be propagated to S100. So one way will be to configure route policies on R2 so that R2 will only advertise some specific prefixes to R3. But if you do so, what if R3 now requires some new prefixes? It means we need to make configuration changes on R2 also. So we make configuration change on R3, we also make configuration change on R2, and this one could disrupt the stability of the network. So that's why we are demonstrating how to use the BGP outbound route filtering feature to ensure that we can efficiently exchange routes without disrupting the flow of the network. So to implement this feature, we need to make some configuration changes. The first thing that we need to do is we need to configure prefixes on R3 to specify which IP prefixes we want to receive. So on R3, let me undo terminal monitor. On R3, what I will do is I need to configure an IP prefixes to specify which IP addresses I want to receive. So I will do IP prefix. I'll call it import. And then I only need to, so index 5, and then I need to permit 100.100.100.100 mask is 32. I will recall the same command and configure index 10 permit 200.200.200.200 mask is 32. So we only want to receive these two prefixes for now. Once we have configured the prefixes, we can now modify our BGP configurations to allow us to exchange the ORF capability between the two routers, and also to configure kind of a policy that will only import the specific route that we have configured from R2. So under BGP, if I display this, you can see that we have these configurations. So I will specify peer 10.10.10.3. Then we are using IP prefix. The IP prefix is import. And then we are importing. So because we want to install these routes in our routing table, so we are using the import. Once we have done this, now we can activate the capability for the routers to advertise ORF feature between R3 and R2. So the command will still be peer 10.10.10.3, and we have this capability advertise. We need to advertise ORF IP prefix. You see that we have receive and send, ORF to be received, ORF to be sent. We'll be using both, so that we are supporting both receiving and sending ORF messages. So I'll use both. But before I do that, we are capturing some packets. Let me see. Let me start capturing packets between these two routers. Start capture, and we'll filter only BGP messages. So we'll do BGP. Then I will run this command. So when we run this command, the BGP session will be re-established again. So it's better when you implement your BGP network during the design, you also have to do this part so that you avoid your sessions re-establishing again. So you can see that we now have the capability advertise ORF, display this. We have these two commands that we have added. And once we've done this, we also need to do a similar, we need to do some configurations on R2. So if I run display BGP peer, you can see that our BGP session is down. I will do BGP 200, and then peer 10.10.10.2. We also need to allow the capability to advertise ORF IP prefix both. So display this is the only command, because we'll be using the IP prefixes sent from R3. So we only need this command for this router to be able to process the ORF messages that will be coming from R3. So display BGP peer. We give it some time to come up. So the peer relationship is now up. So remember before, this router was sending all the routes to from R2 to R3. So let's check. But again, let's check the message exchange between the two. You can see that we have route refresh messages coming in. In the route refresh message, we have the ORF information. So this is what we are looking at. So if we now display BGP routing table peer 10.10.10.2 advertised, you can see that we are only advertising the two routes that have been requested from R2, R3. R3 display BGP routing table peer 10.10.10.3 received routes. You see that we are only receiving these two routes from R2. The ISP is now sending just the specific route that we have requested him to send to our router. And from this one, you can see that we have the route exchange messages now coming in with the ORF message. So another thing now, once you see that we are only getting the two, if we want to receive the third one, maybe 200 or 200 or 210, we can just adjust the prefix that we have on this router, display current configuration, include prefix. So we only need to configure another IP prefix, IP prefix, import. We call it index 15, permit 200 or 200 or 200.210. Mask is 32. So once we do this, we expect to receive another route refresh message. So we are getting other route refresh messages. Normal route refresh request. And if I run the same command, you can see that now we are getting these 200 or 210. The service provider hasn't done anything. When you check on R2, the advertised routes, you can see now this route has been added to our routing policy. So the service provider, the router in the service provider network, is able to process the route refresh message that is coming from R3, and from the outbound route filtering policy that the service provider receives from R3, it's able to filter the routes that the customer network or the customer device has requested only. Nothing like advertising everything from R2 to R3. So you can see that this is a very important feature, and it can efficiently help to reduce the configuration workload and even to efficiently manage the resources that we are using between R2 and R3, because we have reduced the route processing between the two routers. So whenever we want to add another prefix, we just need to add these prefixes on this router, and then it will be able to send a route refresh messages from R3 to R2, and then R2 will process it and only set the route that we have requested. For example, if I delete one of the prefixes, if I do IP prefix import, then I delete index 10. So definitely we expect to receive another route refresh message from R3 to R2. And on R2, if I check advertised routes, you can see that now R2 is only advertising two routes from R2 to R3. R3 also will only receive the two routes advertised from R2 to R3. So this is a very important feature that you can deploy in your network, especially if you are having PECE routing protocol configured as BGP. Then it will help you to reduce the number of routes that are being exchanged between the two routers without doing any policy configurations on the service provider networks. So I hope you've enjoyed this session. I hope you've learned something new, and I hope to see you in our next episode. Just a reminder that if you've enjoyed the session and you are yet to subscribe to our channel, kindly hit that subscribe button, and we'll see you in our next episode. Bye.